In the last segment, I introduced energy, and I hope that what you're seeing is that our process is very similar. Most of the problems, except for temperature, start with some given or starting place, some kind of ending place unit, and then your job is to figure out what the conversion factors are. Largely, a large percent of what we do in chemistry is no different than what we've done so far. Density is no different. It is a derived unit, mass per volume. So we have grams per milliliter, grams per cc, cubic centimeter, grams per liter, and that should alert you that you can use density as a conversion factor. Sometimes you have to figure out what the density is, such as this problem here. Density is grams per milliliter or some volume unit. So we're given grams, 1.25, volume 0.976. So sometimes we have to figure something out before we convert. So 1.25 divided by 0.976, 1.28 grams per milliliter. Be sure you use your sig figs rules. 3 here, 3 here, 3 here. On the next page, sometimes we have to use our density to convert. Density is never a starting place because density is density regardless of the sample size. What mass in grams do I have if I have 25 milliliters of Al? Now, of course, aluminum would not be milliliters, it would probably be cubic centimeters, but nonetheless, our starting place is 25 milliliters. Our ending place is grams. So our process is the same. Then we use our density. Milliliters to gram, volume to mass always means density. 2.4 grams per milliliter. Milliliters will cancel according to the factor label method. 25 times 2.4 is 60. 2 sig figs, 2 sig figs, 2 sig figs. By the way, this is measured, which means this is not an infinite number of significant figures. It is measured, and you have to account for sig figs and something like that. You want 100 milligrams of gold if the density, okay, so density is density regardless of the sample size. What volume? So starting place is 100 milligrams. Notice the decimal. That means 3 sig figs. Volume. You need a volume unit. So since this is in cc's, you should leave this in cc's. Again, we have gram per centimeter cubed. So we have to go milligram to gram and then gram to cc. That's how you let the units do all the work for you. 1,000 milligrams per gram, 19.3 grams per 1 cc. And most of what you do will be the same process. So get out your calculator. And you should get 0.00518 on your calculator. 3 sig figs here. This is a definition. 3 sig figs here. So our answer should have 3 significant figures, and our answer 0.00518. Now, as a matter of standard practice, usually and typically, I will take my calculator answer and put it up on top, and then my final answer I'll put a box around. All right, so the last one on this page is a different application. An unknown is something we're going to be looking at in the lab. If you have something that's unknown, you have to compare it to something that you do know. Okay, so we have a mass and a volume. So density is 1.25 grams, 1.25 milliliters. Our density of our unknown is 1.00 grams per milliliter. And what that means then is that you can't tell anything about an unknown unless you compare it to something that you do know. So you would look up known density. So you would find it in a table somewhere. Okay, so part of what you need to do in chemistry is to recognize what you don't know and that you have to figure out something that you do know. So you would look this up in a density table, and the density table would tell you that this is likely water. Okay? So I bring this up for several reasons. One is that knowing the density of water is a really, really useful thing, because most people measure water in volume, but sometimes you need its mass. So this is a useful factoid that you should commit to memory. Okay? Now, another derived unit is specific gravity, and specific gravity is used a lot in the medical profession. So since many of you are here for medical professions, we like to include this. Okay? It is the ratio between the density of a substance and the density of water. So X grams per milliliter divided by the density of water, which is 1. Notice that the units cancel, so specific gravity is really the density of that substance under normal circumstances. Okay? So if you're given specific gravity, you know numerically it is equal to the density. Okay, so if you have a substance that has a density of 0.975 grams per milliliter, its specific gravity is simply 0.975. Okay? There's no trick here. A 1.00 milliliter urine sample has a mass of 1.05 grams. So that means its density is 1.05 grams, 1.00 milliliters, or 1.05 grams per milliliter. Then it says the normal specific gravity is less than 1.03. Is this sample normal? Okay, so if the density is 1.05 grams per milliliter, therefore the specific gravity is 1.05. So no, specific gravity is not normal because it's greater than 1.03. Okay? And then a thought question. If a 1 milliliter sample was used, 1.0 is only two significant figures. So density, 1.04 grams, 1.0 milliliters, 1.04 grams per milliliter, rounded to sig figs, only gives us two significant figures. And therefore, your measuring device was not good enough to discern whether this is normal or abnormal. Because 1.03, 1.04, 1.02, 1.01, all of those round to 1.0 to two significant figures. These are normal, these are not normal. And this is a good illustration of how your measuring device and your significant figures will tell you something that you need to know.